here. Thanks everybody for joining. My name is Michael Molina. I'm the librarian at Transportation Library in Oklahoma and also with Southern Plains Transportation Center. And today we're going to have two presentations by our Dissertation and Thesis Award winners. They are Noor Hussain and Daniel Stagg. We're going to go with Noor Hussain first. He's going to present on his work, and then Daniel, and afterwards we'll do a joint question and answer session with everybody. So I'll go ahead and let Noor take it away and start talking about his research.
Thank you, Michael. Good afternoon, everybody. This is Noor Hussain. I worked with Dr. Zaman. I finished my master's with Dr. Musharraf Zaman in 2008-2010, and then I started my part-time PhD with him in 2014 and finished. Actually, yesterday was the was 1 year anniversary of my dissertation defense. I defended back in August 2017 on 16th of August, actually. So thanks a lot, Dr. Zaman and SPTC and Oklahoma Department of Transportation for funding this research and giving me the opportunity to pursue my PhD. So the topic of my PhD is, as you can see it here, mechanistic input parameters and model calibration for design and performance evaluation of flexible pavements in Oklahoma. So currently I'm working as a senior project manager in GeoCal. We are about a 60-people farm here in Colorado, and we do a lot of work with Colorado Department of Transportation in these MEPDG sectors, and also a lot of geotechnical and bridge design with the Colorado Department of Transportation and other local agencies. So with that, I would start. So the presentation, I know it's a big presentation, and I'll try to keep it short. In some slides, I will probably go pretty fast. So just to stop me if you guys have any questions. So its introduction, objective, field test facility and data collection, then development of mechanistic empirical pavement design guides, input parameters, sensitivity of the traffic inputs, and we also looked into the contribution of different layers to routing, local calibration of the existing MEPDG models, and with that I would conclude with the conclusion. So basically, as you can see here, just a brief introduction between the MEPDG and AASHTO 1993. As our pavement community, we know that 1993 we have been using since 1950s, but it has been changed or improved quite a bit over the years. But 1993 is basically an empirical design method, whereas mechanistic empirical pavement design, it's more like a mechanistic method which refers to the application and of principles of engineering. For 1993, there was no way of evaluating the performance criteria of how that particular pavement that you are designing would hold up in the real world, whereas MEPDG, it shows you the performance criteria and shows you the graph, like how much would be your pavement distresses over a period of time. 1993 was kind of like 20-year design method mostly, but we can have now a longer design time frame with MEPDG. And when this 1993 was developed, it was actually based on the Asher Road test back in 1950, 1960 time frame, whereas MEPDG is more recent and it has been being developed for over 20 years of design and research experience of the entire U.S. and North America, I should say. So it's more close to the actual traffic materials and climate data, because in 1993 we could not use a climate data, but on MEPDG we are using the actual climate data of the existing conditions. And also the actual benefit, getting the full benefit of MEPDG can be challenging because it is more involved design. You have to input the traffic, climate, and materials all in a separate level. And also they have 3 different levels of input. One is level 1, one is level 2, and level 3. So basically level 1 is the highest accuracy. When you have the site-specific data, then you actually input all this data for site-specific traffic, whatever material you will be constructing your pavement with. you need to have the specific test data available to be able to design on a level 1. Level 3 is just as if you are operating this software in a default mode, so it has those parameters, but also at the same time it has the least accuracy level. And level 2 is the intermediate between the level 1. You may have some level 1 data, may have some level 3 data, so that incorporates a level 2 design. So the challenges in MEPDG is developing these level 1 inputs are very exhaustive and very excruciating time process. This data needs to be quality checked. It needs to have the sophisticated lab testing for asphalt and concrete both. And then the performance model needs local calibration, and also it needs some validation, because whatever works for Oklahoma doesn't work for North State like in Michigan or Illinois. At the same time, whatever works for Illinois doesn't work for Western United States or in Texas. So everything needs to be calibrated to fit the local condition, and that contribution of different layers to pavement distresses, like what layers contribute for your rutting, what layers contribute to your cracking for that specific condition, it needs to be checked as well. So the very important questions that actually posed me to, or actually encouraged me to go through to pursue this research was, is it really important to develop the level 1 input parameters? As you know, like you can use level 3, level 2, level 1. So what is the level of significance to develop the level 1 input parameters? I tried to pursue or try to find out the answer to that question. And if it is really important, then what are the most sensitive parameters? As you know, there are 3 different inputs for traffic, climate, and material. So which one is more sensitive? And after that, is the calibration of the distress models really required? Like, how much difference would you find if your models are not calibrated versus if your models are calibrated? How much level of confidence you have in your design from different calibration aspects, and how these pavement layers are contributing to rutting actually, because as you will see that in the test section that we use for this, for my dissertation, it experienced mostly rutting and International Roughness Index, which is roughness. It did not involve much cracking in it. So to get the answers to those questions, we went ahead and constructed a 1,000-foot long test section on the right-bound lane, which is. Excuse me.
If you wanted it on a different day or a different place, that's fine. Just let us know.
Oh, everyone, make sure you mute yourself so we'll be able to hear Noor's presentation.
Be a cheap lunch for everybody.
Okay, go ahead, Noor.
Okay, so we constructed a 1,000-foot long test sections on I-35. It's in Purcell. It's on the right lane on the southbound direction as if you're going to Dallas, and Oklahoma Department of Transportation, also National Center of Asphalt Technology made a huge contribution for the construction of this and instrumentation of this test section. So we are using this test section to get all our data for level 1 traffic and level 1 materials. Also, we are using a real-life traffic data. So this pavement was open to traffic for about 6 years, and we collected the data for all 6 years. But for the first 4 years, we have actually used for the traffic data and the materials data. But we use the performance data for all the 6 years from 2008 to 2014. As you know, like those are the objectives that that was in my research. Was we developed this level 1 input parameters, and then to look into the sensitivity, we calibrated the models and we evaluated the different layers to rutting. So the methods we used for MEPDG input parameters was, as I was saying, like we collected the traffic data for about 4 years from the weigh-in motion station. Then we used that data for analyzing that data using a software. It's called Traffic Operations and Planning Software. what the software does is it actually differentiates what is the loading of the material of the vehicles that passes, how many axles, and how much is the wheel wander, and every information that is passing through that pavement, every traffic that is passing through that pavement. And after we analyzing with that software, since it's a big software, we actually analyzed that with the MySQL database. And then we wrote a program for that, and that's how we developed the traffic data for different inputs. Because inside the traffic, there are different inputs. Like it's not only average daily truck traffic, but it also monthly adjustment factors, like hourly distribution factors, the vehicle class distribution factor. Axle load spectra is the major deviation from the E-cell-based design from 1993. 1993 had an equivalent single axle load, but now it's axle load spectra, growth rate, and lateral wander. We also use the climate data, so from interpolating from the nearby 6 weather station, we could get the climate data for that particular test section that we are into consideration. Also, we developed that MEPDG input parameters using the materials, the same materials that the test section was being constructed with. We used the same materials and tested in the lab to get the dynamic modulus data for asphalt layers. We have 2 asphalt layers. As you can see here, we have 2-inch PG64-22 top layer, and then we have a bottom asphalt layer, or 2 layers of asphalt. One is 3-inch, another one is 2-inch thick. Total of 5-inch thick asphalt layer with S3 mix with PG64-22 binder. Then we have 8 inches of aggregate base type A, and then we had 8 inches of stabilized subgrade layer with 12% of Class C fly ash we used for it. So we have actually tested all the dynamic modulus data and resonant modulus data for these materials to come up with our level 1 input parameters. And this is a sketch of the test section as you are seeing here. There is lateral positioning sensors here. That's how the vehicles are. These are picking up the vehicles, and these are the strain gauges, and all this is the wind station. So going quick, we had the field test of this test section for about 6 years. We have every 3 months. We are closing down the traffic, and Parcel District, ODOT Region 3, or Division 3 really helped us a lot for closing down the lane. So we measured rod data using this phase dipstick, and we also measured the IRI, the International Roughness Index, and we also measured the crack. We also mapped the cracks. So as you can see here from the data, this is a plot of the 6 years data for rutting. As you can see here, the highest rut was observed about 0.9 inch, which is almost about an inch data, and that's significant rutting for an interstate highway. We also had IRI data. It started really low at about 64 when it's virgin, and then after 5 years or 6 years, it's about 160 inch per mile. And then there was not much of cracking. It was only on the first 100 feet of the test section. And we calculated based on the input data, as you showed, that we using the top software, we calculated the traffic growth rate, which came out to be about 3%, 2.78%, and we also see the distribution of different traffic. So as you can see here, the Class 9 vehicles, FHW Class 9 vehicle was the most heavily traveled vehicle in the test section, followed by the Class 5 vehicle. And we also compared with the level 3, which is the default parameters, as you can see here, that these black lines are the level 1, level 3, which are default, and the colored line are the level 1. As you can see, there is quite a bit of change between level 1 and level 3. We also did the monthly adjustment factors, and as you can see here, this straight line is just the level 3 default data, but in real world, there are a lot of variations between the monthly traffic patterns. The same thing happened with the hourly distribution factors as well. So this is the most important thing. One is the axle load spectra. So this is for the single axles for for Class 9 vehicles. As you can see it here, the default data is about this, but the actual distribution is peak is much higher, and it's more skewed than the normal distribution of the default data. The same thing happens with the like the tandem axles. As you can see it here, it's much different from the default values. So that actually creates a lot of variation in the pavement. Also, the mean data for lateral wheel wander, how much the vehicle actually is moving or shifting inside the lane while it's traveling, there were some variations there as well. And I don't want you to read too much into it, but this is just the materials data that we developed from dynamic modulus data, level 1 for S3, S4 mixes. For asphalt binders, we also had the G star and fine delta for that PG64-22 binder. And we also calculated, we also run the resident modulus test for aggregate-based stabilized subgrade and natural subgrade. And these are the values that you can see from our test results. As you can see it here, our stabilized subgrade was really high with resident modulus. You see varies between 57,000 to about 96,000, so which is very strong layer, whereas your ag base was, the average was probably 30,000. Your natural subgrade with the optimum moisture content plus 2% was 17,000, whereas optimum moisture content was 12,000 PSI resident modulus. So now the question was, one of the questions was whether whether it's sensitive, whether we need to develop the level 1 input parameter. So the answer relies, as you can see it here, on my x-axis this is predicted rod, and on my y-axis this is measured rod. As you can see it here, there is a difference between predicted and measured for about 37% when we use the level 3, the default value for both materials and traffic. Now, when you take the materials as level 1 and keep the traffic as level 3, you see the difference between the predicted and measured is coming down to average about 30%. Now, if you just change that and a permutation combination scenario, when you use level 3 materials and use level 1 traffic, you see the difference between the measured and predicted comes down even less, 16%. So it's, and this is the equality line, as you can see in all these figures. These are going closer to the predicted and measured. That means whatever you are predicting is pretty close to whatever you are measured. And then when you are using both level 1 materials and traffic inputs, you see the average difference is very low, only 10%. So you have very high level of confidence when you are using both level 1 and level 1 materials and traffic. And from this exercise, we also knew that traffic inputs for this particular test section were more sensitive than the materials input for this particular test section for this particular condition. And we also wanted to look, okay, if the traffic was more sensitive, then which traffic input parameters were more sensitive, and we found out that axle load spectra were more sensitive within the traffic input parameters. And then we also decided to calibrate the rod model to see if we can even minimize the error in prediction. These are rod prediction model and asphalt layer. This slide is busy, but I don't want you to like look too deep into it, but there the main calibration factors that we are dealing with is beta R1, then beta R2, and beta R3 basically. So and that's for asphalt layer, and for base layers we have this beta S1. And then the method we calibrated was, we first compared the predicted rod with the field rod, and if the error was significant, then we say, okay, we change one calibration factor at a time and then rerun the calibration process again. If it's still there significant, then we change another parameters and then rerun the calibration until we get to a point where the difference between the predicted and calculated is pretty small, and then that would be our final calibration factor. So we found out that this combination with beta R12, beta R21, beta R3.9, and 1.5 gives you the lowest error, which is error is less than 5%, as you can see it, and the highest R squared value. And you can see it here. After calibration, it is coming to be almost linear. X-squared value is 0.9, and Y is almost equals to X. And then we wanted to do a forensic study and to figure out the contribution of layers of different layers to rutting, and we compared it with a very comprehensive NCHRP study that was performed before. We found out we did and again a huge thanks to ODOT and for facilitating this forensic study. So we did the trenching operation. We cut the cores, we drilled the cores on top of on a crack, and we also measured the rutting. So from that, this is, I know the time is limited, so I'll just move quickly on this. As you can see it here, that when we contribute or when we put together the layer settlement or rut, which is actually a vertical compression of the layer, you can see it here that most of the rutting is confined into the top layer, which is the S4 layer. This is the top lip of the S3, the bottom lip of the S3. There's not much variation here. This is the top of the ag base, but this can be attributed to natural variation for when you're doing the like constructing the pavement. So from this study, we find out that since we have a very strong S3 layer, and we have a stabilized subgrade layer, which is very strong as well, as you can see that 57,000 PSI resilient modulus. So rut was mostly confined in the top layer, which is the S4 layer. So from this exercise, we know like we would better just calibrate only for the asphalt layers, because looks like your ag base and stabilized or subgrade layer does not need much calibration because they did not contribute much towards the rutting. And from this data, we again did a local calibration, and we found out these coefficients for the pavement, which is for this type of pavement in Oklahoma. And this is just like a comparative analysis between what factors we got from the total rut approach versus layer-wise rut approach. So the conclusion was there was not much cracking, but there was significant rutting observed, and the rut was mostly accumulated in the summer months. However, the rate of rutting in the first summer months were much higher than in the second summer months. The MEPDG itself over-predicted the rut about 30% when you were using the level 3, but when you were using the level 1, then your error in prediction reduced to about 10%, which is very, very, very good improvement. So that provides the fact, that kind of verifies the fact that we need to use level 1 parameters for more precision. And within the level 1 parameters for traffic, if you are focusing on traffic, then you should focus on developing the axle load spectra, because that's more sensitive towards the traffic input parameters. And that we also figured out that because from the forensic study is that since we have the stabilized subgrade layer and the HMA layer with RAP, about 25% RAP, so those two things actually work to keep the rutting very minimum only in the top layer. So what we learned from this section is if we can do a 2-inch mill and overlay, that can extend your pavement life quite significantly, since your rutting is mostly confined on the top layer, so which saves a lot of money down the road for ODOT, for maintenance positions, for maintenance aspect of it. And we also have this final calibration coefficient. So since this was the first ever test section and first ever study like that at ODOT or in Oklahoma, we recommend that the factors needs to be validated for more test sections towards Oklahoma, as has been done in other DOTs like Colorado, Texas, and Minnesota, and some other DOTs, and they come up with a more robust models for their pavement maintenance. So I would like to thank Dr. Musharraf Zaman. He's a father figure to me, and for his confidence in me and throughout my my professional life as well. I would like to thank Dr. Dharamveer Singh. He was a student of Dr. Zaman as well, but right now he's an associate professor for Indian Institute of Technology. Would like to thank my committee members, Dr. Dasemi, Dr. Miller, Dr. Hatami, Dr. Bowles, and Dr. David Tim of NCAT and the companies that I was associated with, Atkins, Kleinfelder, my now company, GeoCal. And with that, I would take questions or hand it over to Michael. Thanks a lot for your time. I really enjoyed it.
All right. Thank you so much, Noor. We really appreciate it. I'll go ahead and turn it over to Daniel, and then once Daniel's finished, we can do a question and answer session for both participants. So,
sure.
All right. Go ahead and switch over to Daniel. So.
Okay. Can everybody see my screen?
It shows up over here, okay, yeah.
Okay. All right. Well, my name is Daniel Stagg. I am currently working for Golder. We are an environmental and engineering consulting agency. I presented my dissertation, or excuse me, I presented my thesis back in March of 2017. And what my thesis was on was the development of a novel test method and parametric study to understand the adhesion failure mechanism of asphalt sealants. So I'm just going to do a quick introduction of kind of what I went through whenever I was developing this test. And so a little bit of background for, a little bit of background. Crack sealant has been used as road maintenance technique to prevent water from reaching the subgrade. It is not used for the structural purposes of the road to ensure that there isn't going to be any more cracking. Whenever I first started working with it, I thought that it was kind of like a glue that kind of held the road together. But what I found out in doing my research whenever I started getting into this is that it's just used to prevent the water, because whenever water gets into the subgrade, it really deteriorates and causes a lot more cracking and to happen a lot more rapidly. And so what we have found was that it is expected to extend the life of the roads up to 3 to 5 years without having to completely redo it. But many times it was failing within the first year. And there are 3 different failure methods that can happen. There's adhesive failure, where the crack sealant will actually fail from the side of the wall. So right here in the middle right here is a crack sealant, and this is the side of the wall. Adhesive is right off the side of that separation. Cohesive failure is whenever it splits in the middle of the sealant itself. And then we could have a mixed failure where it'll have a both adhesive and cohesive failure. And so what I wanted to try to do was, there are test methods that could study with concrete blocks or maybe metal plates to study the sealant, but there weren't any tests to look at the actual asphalt interface between asphalt and the sealant that I had found in my research. And so I wanted to develop a new test method to where we could find a little bit more information on this. So the objective was to develop a new test method, and then after I developed the test method, I wanted to assess and quantify and provide some information and see how what we thought we knew, how it correlated to what is actually happening in the field. And then also looked at I correlated the rheological properties and adhesive strength of the asphalt, of the crack sealant. And so for the rest of this presentation organization, I'm going to talk about the research, a little bit of the research that I did going into it. I'm going to spend a lot of time talking about my methodology and how I developed the test and how the test that I developed should be run. And then I'll go into my results and discussion, and I'll have a conclusion. So I'm going to just talk about some of the research real quick that I did. This chart right here kind of explains the different types of sealant that are used. So we have type 1, 2, 3, and 4 are the 4 main types of sealant that are used in asphalt roads today. If you look at it, type 1, 2, and 3 are generally fairly the same, and then type 4, you can see in cone penetration, it has a little bit higher penetration, and then where you really see a big difference is where it extends up to 50% for types 1, 2, and 3, but then type 4 it extends up to 200%. And so this is a little bit of information that I use in the back of my mind of how my tests, whenever I do start running tests, of how it should look. And just for a little bit more background information, type 1s, 2, and 3s are usually used in a little bit warmer climates, and then type 4 is used for extremely cold climates. And so that is the reason why it will have a little bit more extension, a little bit more ability to extend. So I looked at a lot of the other different tests that have been used to study crack sealant, and one of the tests I found that was the most beneficial for me, it was done by Zhao, and where he utilized an overlay tester, and the overlay tester is this rig right here. And I was able to incorporate this overlay tester into my test, but what he used was he used 2 metal surfaces that he attached a crack sealant to and then pulled it apart. And so I modified this, and I'll get into it later, but I used a lot of the information from him, or I used his overlay jig that he used and try to find a way to put asphalt and make it stick to that. That way we weren't necessarily putting as much stress on the sealant. So the need for a new test. As I said, I was trying to do a study on the actual asphalt surface and not necessarily concrete or metal. And so through this, and so that was the purpose for the study. So now I'm going to start talking about my methodology. So what I did in the end, there are going to be different methodology parts. So I did my own asphalt preparation, and so since I did my own asphalt preparation, I had to cut the asphalt to how I wanted it to be so I could have a standard size of what I was using, and then I would have to prepare the sealant, and then the gluing of the sample to the base plate was very important, the test run, cleaning of the base plates, and test matrix. So I'm about to get into the actual details of each of these. So for asphalt preparation, Amethyst was able to provide me a mixture of asphalt that they're using in their roads today. And what I would do is I would get about 4,500 grams of that asphalt mixture and put it in the oven to where it would be heated. And then I would use a gyratory compactor at 60 gyrations. And that would give me approximately the right amount of air voids of what is used out in the field for my lab test. And so after everything is done, it would look like this right here after it is compacted. And so, but from this right here, I would the cylinder right here, I would cut it down into this is what the final product is going to look like. And as you can see, there isn't exclusive asphalt binder that you can just see. We are able to get a mixture of the rocks and the mixture of the asphalt binder. And this helped in developing our test, because whenever asphalt cracks in the road and you put the sealant in between, it's going to bond to whatever is on the face. And so I was able to create a scenario to where it would bond with both the rocks and the asphalt binder. And so going back to the cylinder, what I had to do was I used pretty much a tile cutter, which a tile saw, which shot water into the saw so that it wouldn't overheat. But I made several different cuts, and the first cut I made was along this line right here, and then it would turn into look like this. And so this is the view after the first cut. I took off the sides, and then the second cut that I made, I would trim off the top edges to where the only asphalt part left was this right here. Sorry, did not mean to do that. My next cut would be right across this line right here, going across to where I pretty much have a rectangle. Now from this, I could get approximately 2 to 3 samples depending on how thick the sample was. And so I would measure 1.5 inches out until this is, as you can see right here, it's 1.5 inches thick for one sample. And then I would cut it right in the middle to where one sample would be right here. So this is an example of 2 samples that I have. And so this is just a very basic operation process that I went through in developing my asphalt. So after this, I would clean off the blocks and I would put it in the oven and let it dry so that there wasn't any water that would be on the asphalt, so that whenever I'm applying the crack sealant, it wouldn't, as we all know, water negatively affects negatively affects how crack sealant can bond to the asphalt surfaces, and so I would let it dry in the oven at about for overnight for about 24 hours at a temperature to where it would not melt the asphalt binder or the asphalt that I had created. Now I'm going to talk about my sealant preparation, and this is where this process right here took me a while to develop. And in my matrix that we'll see later, there were two different preparations that I did. I had a thin sample preparation, which is I'm trying to get it as thin as possible to where you can't hardly even see the sealant that is in between it. And then I did a thick sample preparation where I measured out different sizes. And I'll get to my sizes later that I used, but I'm going to tell you all the process of how I did each of these. So for my thin sample preparation, the first thing that I did after the asphalt blocks had been heated was I wanted to create a space that was going to be consistent throughout all my tests. And so I did a 1.5 inch by 1.5 inch area where I would apply the sealant. And how I did this I used Gorilla Tape to place over the edges of the asphalt so that whenever I would pour the sealant, I could wipe it off, and then as you can see right here, I'm pouring the sealant right here. And what I did after that, and it's important to place it on one side of the tape so that you can spread the sealant downwards, and you can get an even placement of the sealant. And how I spread the sealant was I used a metal plate that I had heated to spread it across. And you can see the process right here. I would try to get it in one swipe if I could, but sometimes it would take two. But I would have spread the asphalt sealant over the entire block, and then after I had done that, I was able to tear the pieces of asphalt off, or excuse me, peel the pieces of tape off, and then I'm left with a 1.5 section by 1.5 section, as you can see on the sample right here. And then what I was able to do, I was able to match those two sections together, and then I would let it cure for, I'd let it cure for overnight for 24 hours, and I used a clamp to keep it together so that there wouldn't be any shifting in the asphalt sealant. And as you can see, this is a very thin sample. You can't really see the sealant in between, but it is a 1.5 inch by 1.5 inch section that is being tested for all of my thin samples. Now I'm going to talk about how I prepared my thick samples. And so the first thing that I did was I got a piece of plastic that had the thickness that I wanted to measure, and I would use foil to put on the side of it so that whenever I wanted to remove, so this was used as a spacer in between the asphalt sealant, and it wasn't going to be a part of the test, but so I created foil and I put petroleum jelly on the side of the foil so that whenever I'm placing it in between and I pour the asphalt into this section right here, it would not stick to the surface. That was one thing that I found is whenever I didn't use the petroleum jelly or foil, whenever I try to pull apart the plastic from the sealant would sometimes stick to it, and I was afraid that I was messing up my results, and my results weren't being very consistent. But by doing this, I was able to have a clean peel, and it didn't seem to affect the shape of the sealant very much. And as you can also tell, I am using a clamp on the sides of it to make sure that the distance in between the two samples is in fact the thickness that I have cut these plastic coverings to. So the next part that I would do for the thick sample, as you can see, there is a little gap right there, and I would just pour the asphalt sealant, the crack sealant, into the crack. And it was important that I would pour a little bit more than what I thought was necessary, because after the sample cooled, what I found was that it would have a decrease or a concave in, and what I worried about was that maybe I wasn't getting the full effect of the crack sealant as I would hope to. And so eventually I got it to where I would have an even space, and it looked like it was just asphalt was smoothed over to the other side of the asphalt with the crack sealant in between. And so that was my basic preparation of all my samples. And the next part that I would do is I would need to glue it to a base plate that I would use for the overlay jig. And as you can tell, I've taken apart the clamp that I had on there. And if you look over here, this is what it's going to look like after it has been glued together. And so we had the 1.5 by 1.5 section width, and since the asphalt block is 1.5 inches thick, it is 1.5 by 1.5 section. And this is the, as I talked about earlier, the overlay jig. I have modified it to where it could be set up with the MTS machine, and the MTS machine was able to correlate the data, record data at whatever rate I wanted to, and I found that a rate of, if I record the data at every second, I was able to get good results, and I was able to get a good curve, in which you will see later. But this is a very intricate. I made a lot of modifications to the Thesis overlay jig. I put a rod in the bottom of it to where it was fixed at the bottom, and then we created a top part right here to where it would screw into the top that would connect to the MTS machine. And then this box that it is in is an environmental chamber so that I could test at different temperatures. And I just used liquid nitrogen that was controlled by the environmental chamber. And so by doing this, I was able to test at room temperature. I was able to test at 32 degrees Fahrenheit, and then I could get down to 0 degrees Fahrenheit. And that was as low as the test that I could do with this setup. But this was a very intricate. This also took me a while to modify everything, all the different tools that we had available at Louisiana Tech, and this is how I was able to develop repeatable results. And so, just to give y'all a quick cleanup of what I had to do. So, one of the major problems was for gluing my asphalt to the base plate. I had tried different things, but every single time I tried to grip the asphalt, it tore apart. And so what I ended up doing was I used an epoxy Loctite to glue to the base plate. And that was one of the novel ideas, new ideas that I came up with, was that by using the epoxy to glue to it, didn't mess up the asphalt, and I was able to focus on the sealant. So at the end of the day, after I had run all the tests, I had to put the base plates back into the oven. And I found that it was easier by doing this. I was able to use a flathead screwdriver that I could get into all the grooves and clean all the epoxy out, and that way I could reuse these base plates and I wouldn't have to continuously purchase new base plates. Alright, so now I'm going to talk about the test matrix that I did. There were two different phases. So the first phase, I pretty much just studied type 1 and type 4 sealant. And we did it at two different thicknesses, and for each of the thicknesses, we measured it at each of these temperatures. And then after I did that, we tried a little bit of water conditioning, loading rate, and we did some rheological tests. And this was kind of the beginning to where I could kind of understand a little bit more of the asphalt properties, and so that whenever I wanted to, and I got into my second phase, I could get into a little bit more detail so I can provide more information to the community. And so in my second phase, I was able to do type 1, sealant 2, and 4, and I used these three different thicknesses at these different temperatures. Sorry. Uh-oh, don't know what this is. Okay. So now I'm going to try to get into my results and discussion. And so in the beginning, as I said, this was a very long process in developing my test. And in the beginning, I saw that there were several occurrences where I didn't get what I wanted. So one of the problems was that I was having results where I would get some spikes, and then all of a sudden, and then I would have some results where it wouldn't go up very high. So this part of the results, the green line right here is an example of a good result, and the black line is a bad result. So what I found was whenever I was developing my methodology for applying the cracked sealant, if I didn't heat the cracked sealant all the way, or I didn't have my blocks cleaned thoroughly or something like that, that was the reason why I was having problems with getting repeatable results. But after many trials and error, I was finally able to get a methodology that worked for the pouring of the sealant, in which I discussed earlier. Another example of some bad results is that I saw that it would break from the base plate. The actual asphalt block would break from the base plate. And so that's why it was very important for me to develop a test method to clean the base plate and make sure that I could have an even coating from the block of the asphalt to the base plate with the Loctite. That was another very long process that it took me a while to learn, because I would be running tests and it would be going great, and then all of a sudden it would pop, but the sealant hadn't cracked yet. And so that is the reason why it was very important to learn the cleaning of the base plates. And so now I'm going to start talking about the different failure patterns. This is a very typical failure pattern for type 1. As you can see, it has a very quick rise and then drops off pretty quickly. Type 2, it has a lot of the same effect, where it rises and then drops very quickly. And then for type 4, as you can see, it elongated for a long time, or it seems like it lasted a long time and elongated, and then all of a sudden it would finally drop off. And this is a comparison of the three different types that we just talked about. And so this black line is type 1, and you can see that it generally has the highest strength, but it doesn't necessarily elongate as long as type 2, which is the green line right here, and then obviously type 4, which is this gray line. It goes on for the longest, but it doesn't have nearly as high of a strength. And so we're going to get into some of my actual data right here. So for phase 1 test results, as I talked about, we did a water conditioning sample. And for type 1 and type 4, you can see that it has a very negative effect, which is kind of in conclusion what we hypothesized whenever we were going into the test. And so that was very good for us to know. And that is why whenever I was preparing my asphalt blocks, it was very important for me to make sure they were completely dry whenever I applied the sealant. And then whenever I got to my loading rate, this was very important, because I wanted to make sure that I was able to have a loading rate that wasn't going to be too fast and put too much stress on the sealant, and I could see and have it relate a little bit more to the field, because in the field the cracks aren't going to just separate at a rate of 10 millimeters per minute. And so this kind of shows how the effect of having a 10 millimeter per minute, 1 millimeter per minute, and 0.1, and you can see that there's a big drop off from 10 to 1, and there isn't as much as a drop off from 1 to 0.1 millimeters per minute. And what I ended up doing for all my tests in phase 2 was I used 0.1 millimeters per minute. All right, now this is the dynamic modulus with respect to temperature, and as you can tell, as the temperature decreases, the stiffness increases. So at lower temperatures, we're going to have a higher dynamic modulus as opposed to higher temperatures. And this was also important for me going into phase 2 results, as it's helped me understand and make sure that everything that I was seeing in phase 2 was correlating with everything that I knew from phase 1. Okay, now this is going to be the most important graph that I did for phase 1, and this is where I got a lot of my research from. And so as I had talked earlier, I was trying to develop a method where I could see the adhesive failure in cracked sealant. And so we have type 1, which is going to be these top lines up here, and then type 4, which is going to be these bottom lines. Type 4 would always fail in adhesive failure, but type 1 would have a mixed mode, which is both adhesive and cohesive, and then all of a sudden, once it reached a certain point, it would just fail cohesively. And that was at approximately 0 degrees Fahrenheit, where it appeared we had the max strength of adhesive failure until it failed cohesively. And so, but as we can tell with type 4, I couldn't get down to a temperature low enough to where I could see the max of where it would go to. But if we would assume that the type 1 failure pattern would kind of be the same for type 4, we would have to go to very low temperatures till we saw the maximum of what type 4 could hold. But these are all the results that I had for type 1. I could see that it would get up, depending on the type of thickness I had, we'd have anywhere from 200 to 300 psi for type 1, whereas for type 4 at 0 degrees, it seemed as if we weren't getting very much strength. But in my later test, we'll be able to look at how the sealants relate to each other. And so now I'm going to get into my phase 2 results. And I'm going to kind of go through these charts pretty quickly because they're going to be very similar. But as we look through these, this is a phase of type 1. And what I did was there were 3 different thicknesses that I used. So I used a very thin sample, and then I used a 6 millimeter sample, and then for my medium thickness, and then I used a 12 millimeter sample for the thickness that I used. And you can see the results right here, and they all generally look like they are staying about the same. And then as the temperature decreases, the strength of it increases. And so that's for type 1. This is going to be the same thing for type 2. It's a little bit more uniform, but we see the same kind of pattern. Now for type 4, it's a little bit different. As you can see, we were having a little bit of a problem with a thin sample, as it just kind of leveled off. But everything else that I ran, all the results seem to be kind of linear. Okay, now we're going to do the comparison of the bond strength with the thickness of the samples for type 1, 2, and 4. And so this is a comparison of the thick samples. And as you can tell, type 1 clearly has the biggest strength at the lowest temperature. But then at 32 degrees Fahrenheit and room temperature, it was they were very close to having the same strength, and there wasn't as much separation. And so that is going to generally be the same thing for each of the samples. This is for my medium thickness. We can kind of see the same thing going on. Type 1 has the strongest, and then type 2 and 4 are obviously decreasing. And then at the higher temperatures, they seem to be working about the same. And then for type 3, or excuse me, for the thin samples, once again, same results. So another property that I looked at was elongation. And as we would think, the elongation at higher temperatures, it would have more elongation. And so this is all the type 1 elongation. We have very low elongation at lower temperatures, and it is all very similar for thick, medium, and thin samples. And then for type 2 elongation, you can see that it actually increased a little bit as the temperature decreased. And then for type 4, this is the best results that I had for elongation. And it makes sense because type 4 has if you remember from the matrix that we looked at earlier, type 4 in the ASTM standard, type 4 has the longest elongation from what they said. And so now that we look at the elongation for all the samples, it is very clear that type 1, okay, so for thin, this is the thin elongation. And there wasn't very much elongation at all. As you can tell, it only goes up to 0.25 inches. But whenever we go to a medium thickness, now we start to see a little bit more of a elongation. We get up to 1.6 inches for type 4. And then the type 1 and type 2 stay about the same as it was with the thin elongation. And then for the thick samples, once again, type 4, it increased even more to about 2.5 inches at the lowest temperature. But as we can see, type 1 and type 2 do not change that much from time to time for each of the temperatures, excuse me. And so, in conclusion, from everything that I looked at, the rheological properties do show a correlation between the stiffness and elongation from type 1 and type 4. And to make sure that my test results were still going to be similar from my first phase and my second phase, I looked at where the stress was the highest, and that's at the lowest temperature, and it was within 30 psi. So that shows that my tests are the same because I ran these 2 phases at 2 different times. I ran phase 1 in October of 2016, I believe, or no, during the summer of 2016, and then I ran phase 2 in the winter of 2016. And so it is showing that even throughout all that time, since I use the same methods, that my tests are still very similar. And then elongation is going to be a huge factor whenever choosing sealant. And so in conclusion, I was able to find a new test method that was able to look at the adhesion strength in asphalt surfaces, and some different things that I think can be cool done with this test and provide more information is we can age the sealant to see how it represents aging in the field. we can actually go out and get recovery of sealant from the field and study the properties of that and see how it correlates to this test. We can place a load and do a relaxation, because what I assume in the field is that the cracks are going to continue to get longer. And so with this test and using the machine that I have, we can develop the test to where we separate it a little bit more, and then we let it sit there for an extended period of time, and we can see how the sealant reacts from that. And then we could also do cyclic loading with this to represent tires passing over the crack, and maybe that little bit of stress will might have an effect on the strength of the sealant. And then we can also vary the asphalt mix properties. So those are a lot of different things that we can do. And I would like to give a special thanks out to everybody for the nomination of this award and for choosing me to have won this award. And then I would like to give a special thanks to Louisiana Tech University. They were very instrumental and supportive in everything that I did. Dr. Hall allowed me to have the equipment that I could go in and use, and Dr. Watsi was my supervisor, and he was very instrumental, very passionate about everything, and he was a very big motivator and kept on motivating me to try to perfect the test as much as possible and provide as much information that I could. He was very passionate about it. And then Arafat Shams was very instrumental in helping me develop my test. He's a student that helped me in running all my tests. I couldn't have done it without him. And then Amethyst provided the asphalt that I used. And I just wanted to give a special thanks. And I'll leave everything up to questions if they're I'm done with my presentation, so.
All right. Thank you so much, Daniel. Appreciate it.
Yes,
yeah,
sir.
Do we have any questions for any of our participants? Make sure to unmute yourself, too, before you start asking any questions. It should be the little red microphone button. Just click on that to unmute, and you should be able to ask questions. Okay, and there's also a chat box, too, if anyone wants to type any questions out. Okay, well, if there aren't any questions right now, we can always take them through email afterwards, and we can forward those on. So I'd like to thank our participants for just joining us today and sharing their research and work. So big thanks to Noor Hussain and Daniel Stagg. We really appreciate you guys taking the time out to talk to everybody today. And we're going to go ahead and save this video, and we're going to put it on our channel and on our website. So if you feel like sharing the video or want that link to it, we can forward that to you so you can send it out to whoever you'd like to view it. So yeah, big thanks to our participants, and thanks everybody for joining. And until next time. Oh, yes, Dr.
Michael, let me just say what. Can you hear me?
Yeah, I can hear you fine.
Okay, I just want to also, this is Musharraf Zaman. I also want to thank both of our presenters for their outstanding job, and congratulations to them, for winning these, dissertation and thesis awards. This is one of the really activities. Our primary goal is to really produce, high quality students. So, thanks to Noor, thanks to Daniel, and we look forward to doing it again. And thanks to others actually for joining, this presentation, and thanks to Michael for arranging this. So I just wanted to, thank everyone before we let everyone go.
Thank you, sir.
Thank you.
Thank you.
And just FYI, our next webinar is going to be on September 25th. So more information to follow about that. So get ready for next month. We'll have another one ready for you. So thanks, everybody, and you guys have a good rest of your day.
Thank you.
Thank you.